Okay, there's a few topics I'd like to discuss with you today. Our first topic is going to be static methods. So in Java, a static method is a method that does not depend on an instance in order to work. So recall from our discussion on objects that a class is merely a template that defines what an object has, what properties it has, and what it can do, its behaviors. An instance is an actual specific usage of that object. So if we look at a circle object, for example, this class defines an instance of a circle, or I'm sorry, this class defines a template for a circle object. If we want to create an instance, then we actually specify specific value for this radius, right? Which we actually do down here. We actually create a very specific circle down here, right? So a static method does not rely on an instance in order to do its job. So what does that mean? That means that we're not allowed to use the this keyword inside of a static method. If you ever feel like you have a need to use this inside of a static method, that means it's actually not really a static method at all. Anytime you have a reference to this, you're defining an instance method in Java. So how do static methods work then? Why do we have them? Well, static methods can only get their information from one place. If they can't get the information from the instance variables, from the properties, then they have to get their information from the input parameters of the method itself. So that's why you often see static methods used to represent mathematical formulas, for example. Let me show you how this works in our circle class. We've got this computation for the area of our circle class that's based on the radius, pi r squared, right? Is the classic formula for the area of a circle. I could actually create a static version of this. It takes in the radius as a double. Remember, I cannot reference the instance variables within a static method. So you see how I reference this radius, this dot radius. I can't do that inside of my static method. So if I want to create a static method to compute the area of a circle, then I have to take that radius in as an input then. That's really my only other option. And so then this should be a double return type, just like my original. And so then we can compute and return the value based on the input parameters that we've received. So math.pi times r will be the area of the circle for our static method. Now, what does this gain us? How does this actually work? What's the whole point of doing this? Well, if I want to compute the area of a circle, but I don't want to have to go through the trouble of creating an instance of a circle in order to do it, I can use this static method. So the way that I use a static method, I don't have an instance, right? There's no instance for me to call this method on. So for this circle down here, right, we see I create this circle. If I wanted to get the area, I have to call it on the instance like this. C, in this case, is an instance of the circle class. GetArea then refers to that specific instance of C, that very specific instance of C. So in other words, the value that I pass into the constructor of C is referred to in GetArea. Now, if I want to use my static method instead, I don't want to use an instance. I don't want to create a new circle, which means I won't have this C value to use or any other value, right? I won't have any other instance to use. I have to call it on the class itself. So I can say circle.getArea. You see IntelliJ is helping me out here. It found this static method, but now I have to input the radius that I want to the method in order for it to be able to work. And this is something you'll commonly see. The name of this method is italicized so that we know it's static. We can also tell it's static because this is a class name out in front. And we know this is a class name because the C in circle is capitalized. So this is how we actually call a static method. And so we can actually print these out just to prove to you that they are in fact behaving the same way. Right, so there's our first call to area. I can remove that now, and then I can also print this one out to show you that they are in fact equivalent. Again, the difference is that this one relies on an instance. This one, since it is static, does not require an instance. It operates purely based off of its input parameters. So let's go ahead and run this very quickly here, just to show you that they are in fact equivalent. Can I run? What class am I? I'm in Circle, so I should be able to run this. What am I doing wrong here? I don't see an option. There's Circle. Let's see if this does it. I might have run the wrong class, as I usually do. Yeah, okay, so it worked. Down here we see the same value printed out twice, so it worked. Our static method works the same way as our non-static method, as our instance method, and we don't have to create an instance in order to use it. Actually, all of the methods that you wrote in C, the functions that you wrote in C, would be considered static because you were not using objects at that point in time. Since they do not require objects in order to run, they would be static, although I'm not as familiar with C. I don't think the concept of static actually exists in the language. Just to really drive this point home, notice that if I try to use this .radius here, it seems like it should make sense. I'm in the class, right? I'm in the Circle class, which has a radius. Right? We see up at the top that the Circle does, in fact, have a radius. But if I try to refer to it, we see that IntelliJ is telling me I cannot refer to this in the context of a static method. So static methods cannot rely on this. They cannot rely on a specific instance of a class. Notice too that main is static, right? Main is the entry point of our program. Main is defined as a static method, which means main does not depend on a particular instance, which makes sense. We want to have a neutral kind of level playing field as our entry point into our Java program that can be used to kick everything off. And so main has to be static. I can create instances in main. Notice I still create instances without any trouble. But main itself does not really belong to a particular class. Therefore, I cannot use this within main. Main is static. Okay? So that's static methods. We're going to see some static methods actually in our next topic, which is the factory pattern. This is probably one of the most common, if not the most common design patterns that you'll see, not just in Java, but anywhere. So when do we want to use a factory pattern? And the answer to that question is pretty much whenever we can get away with it. The factory pattern, as its name kind of implies, is going to give us a place to create objects. So we're going to use the factory to create objects whenever we need them. That way we don't have to manage all of that object creation ourselves. We have a whole separate factory object that manages the creation of our other objects that we need within the code. So commonly factory patterns are used when we have an interface or a subclass in common across multiple sets of classes. You see here I'm referring to the shape interface and the classes that go along with that interface from our interfaces lecture. I've added a third class actually that implements the measurable interface called a triangle, right? And so what I want to do is, down here you see I created this instance of a circle, which is just fine, right? But I could conceive of a program that potentially requires lots of circles and maybe some squares and maybe some triangles and some other shapes too. And I don't want to have to say new circle every single time. I don't want to have to say this every single time. So what I can do instead is create a factory. So let's create a class, a factory class. I'm going to create a class, and this is going to be a measurable factory, actually. So I'll call it that. I'll call it a factory so that I know exactly what design pattern that I'm using. And then inside of this factory, I'm going to start defining some static methods to create the measurable objects that I need. So the first method that I'm going to create, I'll create one for circle first. Public static measurable get circle. So here I've created a method that's going to return a measurable object. I can do this because the circle class implements the measurable interface, right? And what I need it to do is to create a new circle and return that to the user. So here you see I created a new circle to return. It's unhappy with me because if we refer back to the circle class, oops, wrong one, we see that circle requires a radius in order to do its job, but that's okay. I can incorporate that into my measurable factory, right? Double R, and then just pass that information onto the circle so that it can do its job, right? So there's a factory method that I can use to create circles. We'll go ahead and create 2 more of these to create squares and triangles. So here we see square and triangle. And so I'll need to incorporate the appropriate information for those particular classes to do what they need. The square class then needs a length, a double length. So I should, I've already got the double here. I just need to rename it appropriately, right? And make sure that I'm returning a square. Right? And then for a triangle, I actually need 3 sides. So side 1, side 2, and side 3. And so when I create my triangle, I can pass those 3 values in S1, S2, and S3. Why are you mad at me? Triangle does in fact exist. Let's see. Did I type it wrong? What's happened here? I created it in the wrong module. You see, I created it in the interfaces module. That's not what I intended. So I'm just going to drag and drop it back up here where it belongs. My apologies. Okay. Perfect. Now it's happy. Great. You can see our triangle now. Okay. Great. So we've created our factory. The next thing that we should do then is go into one of our classes, into our main method, and use the factory to actually create the objects. So I'll say public static void main. If I want to create a circle now, I'll say measurable. Remember, I'm referring to an interface because it has to match the return type of these static methods here. That's my old circle class. So I'll, create a circle that's going to call this static method from the measurable factory class. And again, to call a static method, we simply include the class name, which in this case is measurable factory. And we call the appropriate method, right? And if I want to, I can, include call to, get area or whatever such thing that I want on this particular circle. And then I could create another line to create a square. If I can type, there we go. And again, with the square, I do also have to give it the length of its sides. And so we see here, I misspelled measurable, of course, right? And so we see here I can then call get area on my square if I want to, right? And so I've created two instances of these objects using my factory, using my measurable factory. So what advantages does this give us? What do we get out of using a factory to create our objects instead of creating the objects ourselves? Well, the first thing I already mentioned, it takes the onus of creating objects off of this particular class. I no longer have to create objects myself. I can rely on the factory to give me a stable and consistent way of creating these objects whenever I need them. So the factory will execute the same code every single time, so the objects that I get back will be consistent. So that's the first advantage. The other advantage is that it decouples the implementation of these classes from where I actually use the particular classes. So this is where I'm using the circle class, where I'm using the square class. Let's say I run this program a few times and it works pretty well, but I decide that the circle class is not really what I need anymore, or the circle class works, but I would like for it to behave a little bit differently. I like for it to work a little bit better. If I want to change how a circle is created, or if I even want to change which circle that I'm using, let's say I create a new circle class, for example, I could come back into this measurable factory and say new circle here to represent a new circle class. This doesn't actually exist, right? But let's say I have a class called new circle. And now everywhere before in my code that I was using this circle class, I'm now using the new implementation of my circle class. And the only thing that I had to change was this single line of code inside of my measurable factory, right? So I've decoupled, in other words, the implementation of the circle is now abstracted out of the classes where the circle is used and is kept inside of this factory. So I can easily swap out the pieces for whatever I would like to use in the future. So that's another great advantage of these factory classes. It makes the code much easier to maintain, much easier. Another nice thing about factory is I can actually have the factory choose what type of object to give me. And that's really what's going to exploit the usage of these interfaces or the subclasses. Let me show you an example of that. I can create one more method in my factory, right? It also returns a measurable. But this time I'm going to call it getShape. And this time, I'm going to take in an input parameter, number of sides. And what I want my factory to do this time is return the appropriate shape based on the number of sides that was requested by the user. So I can just use an if statement to check this. If the number of sides is equal to 1, then I can return a new circle object. Now the problem with this particular approach is that if I want a circle, right, it needs a radius. If I want a square, it needs a length for its size. If I want a triangle, it needs 3 sides, right? There's no way that I can reasonably request that information from the user through the input parameters of this method, right? Because I have no way of knowing whether I need 1 value or 3 values until I actually check and see what the number of sides is. So I don't know how many input parameters I need for the shape until I know what the number of sides, the requested number of sides are. So if you are going to go this route, it means that you will need to adjust these classes. You'll need to stick in a default constructor, in other words, that simply sets the radius to be equal to some default value. Right? So what that default value is will depend on the context. I just made this value up because I need to set the instance variable to something, right? Or perhaps if you wanted to, you could even set this to be null. Actually, no, you cannot. Sorry about that. Never mind. Trying to be too clever. It does need to be a double, right? And then later on, it would probably be good if you created a setter for this, so that the user could then change the radius of the circle after it's been created, in other words. But in order for this new factory method to work, I do need, this default constructor here to create a very generic, a very default version of my circle class, right? So let's finish this example up. If I have 3 number of sides, right? That means they want a triangle. So I can do that. Otherwise, in this particular example, the only other thing that they could want is a square. So I'll just return a new. Actually, let me check the number of sides here. I'll show you what I want to do. Number of sides is equal to 4, right? Then I can say return a new square. If they don't give me a value that's acceptable, well, then that's a problem. That's kind of a data validation problem that we discussed when we talked about exceptions. So I'll throw a new illegal argument exception. And indicate to whoever is using this particular method that they need to give me one of these 3 particular values. So let me just add in those default constructors for triangle and square. I'll just make this an equilateral triangle, and to be consistent, I should really be putting this dot in front of each of these, right? Okay, and then one more for my square, or I'll just say this dot length is equal to 10. Okay, and now my measurable factory is ready to use, right? And so if I go back to my main method over here, right, I could now replace these calls with get shape calls, and these are going to be, more generic. Shape has one side, or a circle has one side, right? I can say get shape for the square as 4 sides, right? And now this code should be equivalent. This code should actually behave the same way as it did before. I suppose I never ran it before, but it should behave the same as it did before. If I run the appropriate one. I ran the wrong file, of course. There we go. That looks much better. Okay. So not only does a factory allow us to abstract out the creation of our objects, it also allows us to choose the appropriate object based on a particular parameter that is supplied by the user or the programmer. Okay. Let me just check my notes here and see where we're at. I know there was at least a couple of other things I wanted to talk to you about in terms of these. Okay, so the last topic that I have on my list today is refactoring. So this is kind of going to lead into the problem set. The next problem set, one of the things I ask you to do is go back and refactor the previous problem set, the problem set about sorting arrays. I want you to go back and refactor that problem set to use this new information, to use this factory pattern in order to create your strategies, in order to create your array sorting strategies. So refactoring is a common, very, very common exercise that programmers do on a regular basis. And so I thought it would be good to spend just a few minutes talking about what refactoring is, when it should be done, and why it's so particularly useful. So why refactor? right, is the first question. And the answer to that is to, make code more maintainable, easier to maintain, let's say, easier to understand, right? And also make it more efficient, potentially. So, at some point in your life, if you haven't already, you're going to write some ugly code. I write ugly code all the time. You may argue that some of the code I've shown you is not particularly beautiful, and I would not necessarily disagree with you. It happens. It's part of programming, is we write code that's not ideal. So when that's the case, usually our mindset is, I just want to get this to work. I just want to make this work so that I can, finish this and move on to the next thing, which is fine. Of course, getting things to work is important. But we do care about making code that's easy to maintain. Someday we're going to have to come back to that code. We're going to have to add something into it, or change it somehow based on a request that came from our users. And if our code is nasty, if our code is ugly, it's going to be hard to track down exactly where those changes need to take place. So that's where refactoring can come into play. This is a very huge topic. I don't have time to do its complete justice. I don't have time to go into this in large amounts of detail. But I just wanted to explain, a couple common times when you might refactor your code and what you should kind of be looking for as you write in terms of refactoring your code. The most common form of refactoring that I suggest to people is repetition. So if we have reasons to refactor, repetition is at the top of the list. As programmers, repeating code should make us feel bad. Honestly, repeating code is not ideal. There's a rule of 3 that's commonly floated about. The first time you need a piece of code, you just write it. You just make it work. The second time you need a piece of code, you copy it and you paste it into the appropriate place, but it should make you feel bad. Anytime you copy code without changing it at all, like you just completely copy and paste, it should make you feel bad. The third time you refactor, the third time you copy code, the third time you need to duplicate code, you should refactor. And so if you're duplicating code more than twice is what the rule says. So if I'm duplicating code 3 or more times, what I should do instead is create a method and move that duplicated code into the method and then call the method in the appropriate place. So if you see lots of repetition, if you see lots of code that's being repeated over and over again, you should abstract that out into a method, right? And then use that method as appropriate. Another common reason to refactor is violating the relationships that we talked about. So in this case, I mean has a, right? Or is a, or can do, right? A lot of you have been very good about following these relationships, but it can get, it is possible to write code that does violate these relationships. In other words, I create a property within a class, but it doesn't make sense within this has a relationship. For example, if I were to say, a person has wheels, or, a cat has a computer, maybe in some weird, absurd world that perhaps makes sense. But in general, those kinds of properties don't fit the classes that they exist within. Is-a is for inheritance, right? And can do is for our interfaces. So those same relationship violations can occur with those as well. If you run across this, if you run across a violation of one of these relationships, then you need to reconsider. In the case of is-a, in the case of inheritance, or in the case of can do, right? You can consider separating the behavior out into a separate interface, into a separate subclass or a separate base class, as the case may be. In the terms of has-a, if I've got a property that I think is in the wrong place, then I'll want to create a new class that does follow this relationship and move those properties into that new class and use the new class as appropriate. So that's that's kind of the second major reason to refactor that I commonly see. And the third major reason that I see for refactoring is what we're talking about right now, what we've been talking about for the last couple of lectures, which is just poor design, which comes in many shapes and forms. We've been talking about it in terms of design patterns, right? If I ever see the new keyword pop up in somebody's code, I expect it to be in a factory class. So if I'm not in a factory class, I should probably have a pretty good reason for that. Otherwise, I should refactor my code. I should go back and refactor the code to create a factory class and incorporate the design pattern so that I gain all the advantages from that particular design pattern that we've discussed. Right. Same thing for a strategy pattern. If I see 5 different methods in a class that do the same thing in 5 different ways, to me that's an indication that I should be using the strategy pattern. And so I would encourage that person or whoever wrote the code, right, to refactor their code, create an interface that utilizes the strategy pattern, and then implement that interface on a set of objects to encapsulate those behaviors. To abstract those behaviors out of the particular class. So design does come in many shapes, many forms, right? Those are just a few small examples. And this one's probably the hardest, right? It can be hard to pick out. It can be very hard to see, right? So just be aware of these reasons to refactor. And then in terms of refactoring itself, right, there's one very important rule. The most important rule of refactoring is don't add anything. Don't add any new features, right? No new features at all while you're refactoring. Refactoring is the process of rewriting your code, but making sure that it has the same behavior, the exact same behavior before you rewrote it as it does after you rewrote it, right? So adding new features is a separate process. If I want to add new functionality to my code, if I want to change how my code works in some particular way, that is an entirely separate process from refactoring. You should never, ever mix the two. The reason for this is because refactoring itself can be particularly complicated. Refactoring can introduce bugs into your code. Refactoring can prevent your code from working. It can break your code, right? Adding new features, the same thing is true. Adding new features to your code can also break it. It can also cause bugs. It can also cause unexpected behavior. So if you're refactoring and adding new features in at the same time, and your code breaks, then what's the problem? It's very hard to track down which of those is the culprit, which of those is responsible for the breakage of your code, right? So if you're refactoring code, the behavior of your code should remain the same. It's only the code, right? It's only the code itself that's changing. It's only the how that's changing. The actual behavior itself does not change during the refactor process. And in order to drive this point home, last point that I'll make about refactoring is use your tests. I've been asking you to write unit tests for every single problem set that you've been working on so far, right? One of the reasons that I have you write tests is for refactoring. If I refactor a piece of code, the tests that pass before the refactor should also pass after the refactor. So I can use my unit tests to give me an indication of whether my refactoring was successful or not. I kind of expect refactoring to break my code at least a little bit. So it should cause some of my tests to fail. That's expected. That's okay, right? But I can use those tests as kind of a guideline to indicate whether or not I've successfully refactored my code, whether I've changed the design of my code, right, without changing the ultimate behavior. Because if it passes all of the tests, then I know that the behavior, at least the behavior that I've tested, is the same before and after the refactor. This is also another reason why it's important to test very thoroughly, important to test every single method. And if refactoring ends up requiring new methods, then you should test those new methods as well. You should create tests for those as well. Otherwise, you won't be able to tell if making a change in your code breaks it or makes it behave in an unexpected way. For problem set 5, the first thing I ask you to do is go back and refactor the previous problem set to utilize this factory pattern. You could actually do this for many of the problem sets that we've been working on if you would like. Once that's done, I ask you to go through an exercise that utilizes both the factory pattern and the strategy pattern. So we're going to kind of tie these two design patterns together. It's going to be robot fights, so robots that attack each other. And so have fun with it. There's actually a lot of room to experiment here. There's a lot of fun. This is one of my favorite exercises, actually. Grab a friend and try your robot strategy out against them and see how well it works. See how well your robot performs versus everybody else. You could probably even get a little tournament going, right, to see who can make the best robot under the given conditions. So take a look at that problem set. And I think that's going to finish up my lecture. So just to review, we covered static methods, right, which are methods that do not depend on an instance of a class. We covered the factory pattern, which allows us to delegate the responsibility for creating objects into one single place, into a single factory class, right? And we discussed why that's important, why that's useful. And then finally, we discussed refactoring code, rewriting your code to make it easier to maintain while maintaining the same behavior that it had before. So thanks very much for watching.